Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 422 problems A to E. And let's first start with problem A. So for problem A, there's a game, and this game has 8 worlds. Each world has 8 stages, and the stages all have an order. So the first stage is 1 in the first world, and the next stage is the jth stage in the ith world. And these describe the rules of these stages. So basically, the stages are represented like this with 2 numbers with a dash in between. And the first number represent the world that the stage is in, and the second number represent the index of the stage. And when we move to the next stage, if this is I and J, so the first number is I, the second number is J. If J is less than 8, then the next stage is J plus 1. So for example, this means that if we're currently on stage 1, 1, then the next stage is going to be 1, 2. And another rule is if J is already equal to 8, then that means that we're already on the 8th stage of the current world. Then the next stage, we'd move to the first stage of the next world. So, for example, if we're currently on 1, 8, then the next stage is going to be 2, 1. And if we're already on 8, 8, then there are no more stages left and there's no next stage. So for this problem, we could directly check these if statements to see if we need to add 1 to the stage or the world. So for example, let's look at sample input 1. For this input, the next stage would just be 4, 3 because we're only on the second stage of this world. And for the next input, we're already on the 8th stage of the first world. So we'd move to 2, 1. The next stage would be 2, 1. And let's look at the code. So here's my code, and I inputted because the input is given as a string, so I inputted each character, and then I inputted like this, so that I would be the world and J would be the stage. And I converted these to integers, but I think I named the stage and world opposite to what the class question is actually is, but then it's just variable names and it doesn't really matter. And so I converted these to integers so I could add them, and yeah, so because these are characters, I did I minus character 0 to get the integer. And here I'm checking the conditions. So this is actually stage, but yeah, so if stage is less than 8, then we will add 1 to stage. And then otherwise, this is the second case where J is already equal to 8 and I is still less than 8. Then we would set the stage to 1 and add 1 to the world. And in the end, we'd print out the answer. Next, let's look at problem B. For problem B, we have a grid with H rows and W columns. And each cell is either white or black, represented by a dot symbol or this crossed symbol. And we want to determine whether for each black cell, the number of adjacent cells that are painted black is 2 or 4. So looking at this example, if we have a black cell, then for example, this black cell, then the adjacent cells would be this one, this one, this one, and this one. Out of these four adjacent cells, only two, the top and the bottom ones, are painted black. So this one will satisfy the constraints. And we want to check for all of these black cells if they all satisfy the constraints. Since the H and W is small, we can directly check this, and let's look at the code. So here is my code, and I first inputted the grid. I defined dx and dy for the moving to four adjacent sides to make finding adjacent cells easier. Then I loop through the entire grid. If the current cell is a black cell, then I'll check all the adjacent cells. So here I looped from D to 0 to 4. This checks all the adjacent cells and find the new indexes, which represents the indexes of the adjacent cells. I check if the index is in the bounds of our grid, and if it is, whether the adjacent cell is also black. If these constraints are satisfied, then I would add 1 to count, representing that the number of adjacent cells that are also black. So if count is not 2 or 4, then we output no, because this means that it doesn't satisfy the constraints, and we could immediately output no and stop the program. If the program runs to the end, then this means that all the black cells satisfy the constraint, and we'd output yes. Next, let's move on to problem C. For problem C, Takahashi has some letters, and each letter he has is either A or B or C. He has NA letters A, NB letters C, letters B, and NC letters C. And he can hold one contest by using a letter A, a letter C, and any other letter. We want to find the maximum number of contests that he can possibly hold. So for example, he could hold a contest with a letter A, a letter C, and then any additional letters. So a letter C would work, a letter B, or an additional letter A would work. So contests AAC, ABC, or like ACC will all work. And we want to find the maximum contests that he can hold if he has these amount of letters. Since this problem is trying to find the maximum, then I solved it using binary search, because maximum and minimum problems give me the idea that we can use binary search. So I did binary search on the maximum number of contests that he can hold. And we can directly look at the code for more detail. So here I inputted the number of A's, the number of B's, the number of C's that he has. And there are T test cases, so I did this for each of the test cases. Then the because NA, NB, and NC have a maximum of 10 to the power of 9, so the maximum number of contests that he can hold is 10 to the power of 9. So the minimum will be 0, and the maximum I set to 10 to the power of 9 plus 1, because in the end I do a minus 1. So this ensures that the edge cases are also correct. So I did binary search on the number of contests that he can hold. Then, so mid is the number of contests that he can hold. So the remaining number of A is NA minus mid because he's already held, like we suppose that he can hold mid amount of contests. Then the number of A's left will be NA minus mid. The number of C's left will be NC minus mid because NA and NC is required for each contest. So if A is greater than 0 and C is greater than 0 and A plus C plus NB is greater than or equal to mid, then this works. The reason we did NB is that the remaining number of B's is still the original number of B's. And so the characters that we still have left after we subtract the required A's and C's is just A plus C, here, A plus C plus NB. And this needs to be greater than or equal to mid because mid is the number of contests that we want to hold, and we're checking if this is possible. So if we want to hold this amount, mid amount of contests, then the remaining number of characters need to be greater than or equal to this number. So if this works, we do the typical binary search where we set the lower bound to mid plus 1, and otherwise we set the upper bound to last equal to mid. And in the end, we print out first minus 1 because first will represent the smallest value that is impossible. So if we subtract 1, then that number is possible. Next, let's talk about problem D. For problem D, we have a positive integer n, and the sequence a from a1 to a2n consists of non-negative integers that sum to a value of k. So a number x is obtained by the operation described here, which is for each x is for each operation, x is updated to the maximum of x and the difference between the maximum in A and minimum in A. So if we look at an example, when n is equal to 2, A has a length of 4. And suppose that it contains these 4 numbers, then the first operation updates x to the max of 0, and then the difference between 8 and 3, where because 8 and 3 is respectively the maximum and the minimum of this current array A. So from this, we get 5. Afterwards, we reset A, we combine the elements, so A becomes 14 and 8. Then we continue, we repeat this operation. So we find the maximum of 5 and 14 minus 8, which is 6. So if the array is equal to 6, 8, 3, 5, then our answer would be 6. So we're given a integer k and a integer n. We want to construct a sequence that minimize the number x. So in the end, we want to output the value x, that is the minimum, and then we want to output the sequence that we constructed. We want to minimize x, and in this case, we can separate the problem into two cases. Case one is if k is divisible by 2 to the power of n, then this means that x will be 0 because each element in the array can just be all the same number. Because the number is divisible, then that means all the elements can be the same and the maximum will equal to the minimum. But then there's another case. Case 2 is if k is not divisible by 2 to the power of n. In this case, we find that x would be equal to 1. And we could show this by induction. So for example, if we currently have a element a, although the operation in the problem is combining the numbers, if we show that for each step, if we split the numbers and then their maximum and minimum for each operation is still has a difference of less than or equal to 1, then this shows that if we combine the numbers, then x would still be equal to 1. So if we first only have one number, a, and if we split into two numbers, then if we want to minimize the difference, we would take the floor function of a divided by 2 and the ceiling of a divided by 2. This difference is less than or equal to 1 because of the properties of this floor and ceiling function. So by this, we show that the base case for induction is satisfied. Then if we move on to another case, then suppose we have some array of length L from A1 to AL. There are three cases for this array. First, if the maximum of this array is equal to the minimum. So if the maximum of this array is equal to the minimum, then this means that all of this array, like all the numbers are equal to some number v. Then if we split all of the numbers, then we would get v divided by 2 floor and v divided by 2 ceiling. Then for this, we would get that this number is the maximum and this number becomes the minimum. And because of the properties of floor and ceiling that we mentioned, then this still satisfies that difference is less than or equal to 1. And let's look at the next case where if the maximum is an odd number and the minimum is a even number, then we will get the maximum can be represented by 2m plus 1 and minimum is 2m. So if this is the case, if we split the minimum 2m, we'd get m and m. If we split 2m plus 1, we get m and m plus 1. This gives that all the values are in the range m to m plus 1. So the difference is still less than or equal to 1. Then for the last case, if the maximum is an even number and the minimum is a odd number, then if we split this number, we get m. If we split this number, we get m minus 1, m. So all the numbers are in the range m minus 1 to n. So the difference is still less than or equal to 1. So for all three cases, we get that the difference would still be less than or equal to 1. And if we continuously repeat this operation, then all the numbers would still satisfy that the difference is less than or equal to 1 when you split them. So we know that for all the operations, the array will have a difference of maximum and minimum less than or equal to 1. So if this is after this, we know that the answer is either 0 or 1. And now we need to construct the array. And we could construct the array by repeatedly dividing each element by 2. So we can start with a single element because the sum is equal to k. We could start with k, and then we will move to k divided by 2, and then k. Then we will continue to split this element and split this element. And in the end, after n operations, we will get our desired array. So a1, a2 to some a2 to the power of n. And let's look at the code. So here's my code. I first created an array to represent the powers of 2, to store the powers of 2, and I inputted the values n and k. To construct the array answer, I first inputted the value k inside answer, and as I described, each time we split all of the values into x divided by 2 floor, and then x minus x divided by 2. This is the ceiling. We split each value, then we set answer to be, and we repeat this operation, splitting each of the values again. Then we can check if k is divisible by 2 to the power of n. If this is, then this means that all the numbers can be equal, and x will be 0. Otherwise, x will be equal to 1. In the end, we print out all the values for answer. Now let's discuss problem E. For problem E, we have n points, and n is an odd number. The ith point is represented as xi, yi, and we want to find if there is a line that can be expressed as ax plus by plus d that passes through more than half of the endpoints. So if we want to find a line, we can choose 2 points. And if we choose 2 points, we can then check if other points pass through the same line. So if other points are on the same line, and if there are more than half of the points that are on that line, then this means that the line satisfies the constraint and we can print out the answer. So if we randomly choose 2 points, because we want the line to pass through at least n plus 1, more than half of the points, and because n is odd, then this more than half will be represented by n plus 1 divided by 2. So the probability of us finding this line, finding some line, will be out of n points, we chose this half points. So this is n plus 1 divided by 2 over n. And because this is without replacement, we choose another distinct point, which is n minus 1, and then n plus 1 divided by 2 minus 1. So for this, we get n plus 1 over 4n, which is 1/4 plus 1 over 4n, which is greater than 1/4. So this means that the probability of getting a wrong answer, so the probability of not finding this line on a specific try is less than 3/4. And if we suppose we randomly choose sometimes, suppose we choose about 30 times, then the probability of would be about 1.78 times 10 to the power of -4. So this value is already small, and you could also find other values. Like you could also try to randomly choose more points, maybe 100 sets of points. Then for each pair of points, we can loop through all the remaining points and check if the 3 points are on the same line. So we can check this by checking if the area is equal to 0. And we could calculate the area of the formed by 3 points. So if it's x1, so suppose these 3 points are on the same line, then it would be something like this instead of this. So that means the area, if like x3, y3 was here, then the area would be equal to 0. So that's why we can check the area. And we can check the area via Shoelace theorem, which can be used to calculate the area of like 3 points. So if this value is equal to 0, then that means the area is equal to 0 and the 3 points are on the same line. So if there are more than half of the points that satisfies this constraint, then we can print out the equation of the line. And let's look at the code. So here's my code, and this function is to randomly choose a pair of points. Then I chose 30 pairs, and so I chose my points, and then x1, y1, x2, y2 are the chosen points. I then loop through all the remaining points, which is called x3, y3, and then I checked if the area is equal to 0. If it is, I added 1 to count, which represents how many points are on the same line. So if count is greater than and divided by 2, then this means that more than half of the points satisfy this constraint. And then I print out the answer where ABC is the formula of the line as asked by the question. So I print out yes, and I print out the value of A, B, and C. Otherwise, I print out no. And thank you for listening to today's explanation.